Swayam Prabha. Digital India. Educated India.
Okay, since we've been talking about large signal blots in the PA, I thought we'd just continue large signal before we go to the LNA. So in most arrays, as we saw in the architecture, we need to provide LO to mixers, right? And as the millimeter wave frequencies are high, necessarily the LO is high as well. So typically what we find is that we have a mixer that requires the LO, right? And if I have a situation where there are multiple mixers that are there, for example, IQ mixers are there, or I have multiple mixers on my chip as well. In general, what we try to do is try to keep the LO distribution frequency low by building a frequency multiplier, right? And building doublers or triplers or quadruplers is pretty common, right? In order to lower the frequency that we have to bring in as the LO to the chip, right? So from a spec range for doublers, or from performance metrics for doublers, we worry about the input frequency range. We would like enough output power in the doubler because it has to drive the mixer. Typically, you might also have a situation where you have the doubler, and then this doubler is going to get to a quadrature block, and so you now have IQ of your LO, right? So that you can do quadrature mixing. So given that this is a passive split, and you still want to be able to drive mixers, right? You need to make sure that the output power of the doubler is enough. I'd like to minimize the input power that is required in order to achieve this. So this is, let's say, at in our convention, this would be at, let's say, some m times f naught. Then this would be the input power that we are applying at the fundamental frequency from which we are trying to get the output power. The doubler would have a concept of efficiency where I can define again equivalent to power added efficiency, or typically I do worry more about P out over PDC, right, in the doubler. And then we would like a low fundamental feed through, right, because we don't want F naught to leak in through here, right? Because if that leaks in, then we are having our mixers are seeing some part of the fundamental as well. And if we have a situation where the doubler requires a high input power in order to, or the frequency multiplier in general requires a high input power, then the leakage will also go into the mixer and cause spurious reception or spurious transmission. And we would overall, in the same spirit, make sure that there is low power at unwanted harmonics, right? Only at the desired harmonics we have power. So given this sort of spec range, there are several ways in which to build the doubler. We can build it using self-mixing, where if I have an input F naught and I feed it to the mixer, there is going to be an output at 2 F naught, right? And I can filter for that output and then be able to get this. There is the option of using nonlinearities in my device, where just as we saw in class B or class C biasing, we are going to get harmonics. So now instead of making the tank resonate at F naught, I made the tank resonate at 2 F naught, so that way I can convert the current, second harmonic current into voltage at the output, right? That's one approach. The challenge with this approach, for example, is that there will be still a reasonable F naught signal, because as you can imagine, with a second order resonator, I might from F0 to 2F0, I might get rejection that's of the order of 6 to 8 dB, right? I mean, it's not going to be substantially large. So a popular topology is to do a push-pull doubler topology where because of just the fundamental nature of the topology, odd harmonics are going to get cancelled at this node. So F0, 3F0, 5F0 will disappear and I'll be left only with the even harmonic currents. So now if I build a filter here that is resonator here that is tuned to 2F0, for example, right, then I can pick up a 2F0 signal and the F0 signal is rejected just by symmetry. There is also the concept of building injection lock doublers where I build an oscillator at 2F0 and then feed it a signal at F0 as an injection signal, and the oscillator will lock on to it and produce a 2F0 signal. Typically, trade-offs as noted here can depend upon the amount of input power you need. For example, pretty low for injection locked oscillators, but on the other hand, it's tough to get high output power unless you try to design some power oscillators. But then, these topologies all have trade-offs. A little bit of intuition here is that if we think about just a square wave with a duty cycle, right? Let's say that this is the period of the square wave. So when you have 50% duty cycle, right, there's going to be a strong fundamental component. But what you can see as you vary the duty cycle is that different harmonics peak at different duty cycles, right? So for example, if I'm building a doubler, it would be nice to get a current waveform that has a duty cycle that is close to 0.2, right? Because then at that point, my second harmonic is going to get emphasized compared to the other harmonics that I have. Similarly, if I'm trying to build a third harmonic system, I should build 15% duty cycle or even 50% duty cycle will work, right? But these kind of curves can help select, for example, where we are biasing the device to create the current waveforms that are coming out, right? So you can decide on that kind of biasing. The other traditional thing that is observed is that a lot of these these doublers suffer. So I am trying to get a high 2F0 signal over here, right? So if imagine that we didn't have the cascade and we were directly at the load, then we would have a high amplitude at 2F0, and then there is feedback capacitances over here, right? So that leads to a 2F0 signal at this node, and that the existence of a large signal there basically starts preventing the F0 signal from being able to drive the IC, so affects matching and affects conversion gain. So one approach is to create a trap here so that the second harmonic waveform doesn't show up, right, at the gates. And this kind of short approach can help build more efficiency and more conversion gain in the frequency multiplier. The other approach that is also taken is that one can leverage it, where the general philosophy is that if I have a doubler scheme like this, a push-pull doubler, if I consider a situation where I'm able to create some kind of short or open at 2F0, right, I can find that there is a point where the coupled signal comes back, adds constructively or destructively, right? And this can help the conversion gain as well. So you can sweep this and look at conversion gain at this node, right, to figure out what the reflector should be. So in this case over here, they built a circuit that's effectively operating at 2f0 in order to create a load here that works well with coupling that is occurring from this node to with the output node. There is also work now where similar to what we were discussing in terms of PAs, we drive both the gate and the source with the F0 signal in these push-pull pairs. The idea here is that because you're driving the source, you are seeing a 1 over GM impedance effectively looking in from here. So this becomes a low Q load. So as a result, you can get very wideband input match. And then with the same push architecture, you can reject the 2f0. And then in this paper, we showed that by looking at this network, right, the way it looks different at f0 and 2f0. So we can configure using these passives to further increase conversion gain from f0 to 2f0. And this gives you the sort of representative performance for what these doublers at millimeter wave can do, right? Because they are, unlike the PA, back off is not a concern here. So you are trying to operate at the peak efficiency point. So you can get efficiencies that are of the order of 30-35% P out efficiencies. And we see here that this, of course, at its peak, there is a loss, right? So effectively, P in at the fundamental is 12 dBm and P out at 2f0 is of the order of 9 dBm, right? So there's a 3 dB reduction, but the minimum input power that you need for this is a lot lower. And the really nice benefit of building these doublers is that you can get really high fractional bandwidth. So you're not concerned by the bandwidth of the LO path. So a wideband coupler that follows this kind of doubler can create a wideband LO quadrature signals that you can use in your transmitters and receivers with a single low frequency LO. So if we have time and we look at some of the array architectures, you will see that a lot of the arrays have some sort of frequency multiplier into them to reduce the input frequency. So that was a very high level view of doublers, right? We'll now move to low noise amplifiers, which is the one of the blocks that we have in the, right? And so what are the key metrics that we worry about when we have the low noise amplifier? Our objective is to make sure that we have a good gain and good noise figure, right? And we, if you remember, we defined noise figure as for any block as SNR in divided by SNR out, right? This can be represented as if we analyze it, it basically shows up as this equation, which basically, if I consider a block, right, and I have at its input some noise source which is NN, right, then the noise figure is basically, if I look at the output, this block is adding some noise, right? So the noise figure in dB, or the noise factor when it's without not on the log scale, on the linear scale, we can express it like this. And I'm assuming knowledge that if you have a cascaded system, right, where you have F1, a block with noise factor F1 and gain G1, and a block with noise factor F2 and gain G2, so on and so forth, right? Your effective noise figure is F1 plus F2 minus 1 divided by G1 plus F3 minus 1 divided by G1, G2, right? And this implies that the first block should have low noise factor and should have high gain to protect the noise of subsequent blocks. So that basically gives us the gain and noise factor spec. We of course have the bandwidth spec. This must be true across the bandwidth of interest, right? And then we also have this constraint, which is that typically this LNA is going to be at the input, and the input is going to be a power source of source impedance Z naught. So I need to be power matched to the system, right? So being power matched would imply that I'm getting as much power as I can from the source, right? So I'd like to be conjugate matched. If I'm not, then what can happen is that the input power comes in and gets reflected and goes back, right? Now there is always this question of can you design this in voltage domain, or because usually this is the chip boundary, right? And there might be another stage, or there might be a mixer, there might be some block following this. And typically these blocks are close enough together that you might start designing them in voltage domain, right? You can design this also in voltage domain. It's fine, you don't need to match, but then you have to be very sure that you know exactly what the cable is going to be between your source and your LNA. You know this entire network very, very precisely, right? And it's not going to change. But when we design the LNA, usually we design the LNA to be used across applications. We don't know exactly what antenna at what distance people are going to build. So if I don't design this as matched, I might have a situation where I have an extreme mismatch between my antenna and my LNA, and I start rejecting all power. So at least at the input stage, we talk about conjugate matching the LNA. At the output stage, we don't need to really conjugate match the LNA. Just as a simple bit of intuition, if at the LNA you have an output impedance R out, right? And let's say that there is some C out over here, and the next stage is R in and C in, right? And let's say all I'm doing is I know that these wires are close together, and I'm just making an L that resonates out, right? So yes, I'm not conjugate matched in the sense that R out is not equal to R in, but the reactive part is resonating out just as it would in a matched network. So I have some loss because R out is not equal to R in terms of losing optimum power out going into the next stage. But if they are similar of the same order of magnitude, then I don't need to worry too much about losses because or suboptimal performance because of this, right? So yes, I'm not conjugate matched, but I'm close. It may not be terribly bad. But where I need to consider even matching at the output stage, if I'm operating in a world where just similar to the input stage, I have the LNA, and then there is some kind of interconnect that is going to the next stage, right? And just from a practical perspective, this block is being designed, this block is being designed at the same time, right? Let's say, for example, that all the amplification is in one stage, and we'll say that this is a mixer, right? And this block is being designed and this block is being designed, and as they are being designed, we don't know where they will be placed in the layout and what the interconnect between them will look like. Then it makes sense for both blocks to be designed to Z naught. This is designed to Z naught, this is designed to Z naught, so that we don't have to worry about what impedance the mixer will present depending upon its location, right? So it's a design simplification process. It's not an essential thing in on-chip design. If I can guarantee placement of the output and full knowledge, or I start designing in a cascaded way where I first design the mixer, then I know the load, I know where I'm going to place this, and then I'm going to design the LNA, design it in voltage domain without conjugate matching, by all means. It will work. That will not be a problem. You will see an RF filter. So because the array is RF in and then RF out, right? So you'd have a filter here going into the mixer, and then at the output of the mixer, you'd have an IF filter, right? So both these filters exist now in systems for various reasons, but this kind of stuff exists. But inside a chip, usually the resonant networks are enough. Yeah, so that's the next logical spec that comes in, which is linearity, because the LNA is the first block in the system. So really strong signal is going to compress it, right? At millimeter wave, the path loss is big enough that the existence of a large signal is not as prevalent as RF. So typically linearity constraints are not that significant. However, in millimeter wave radar, linearity constraints are very significant because that's a full duplex system effectively, or rather I should say not full duplex, a simultaneous transmit and receive system, right? Yeah, I mean, it's, yeah, so since we're not communicating, but effectively, if I have a TH leaking into my RH, this is a very strong signal, right? So then my LNA needs to be very linear. So if you look at millimeter wave radar systems, this LNA actually is very low gain and high noise figure because it needs to handle the strong signal. So that's the trade-off you made. So if you see a communication 60 gigahertz LNA, you will see 3-4 dB noise figure, and then if you see a millimeter wave radar, you will see noise figure in 10 dB range, because the constraint is the linearity of the first stage. So as from this discussion, it becomes clear that there is a trade-off between linearity, noise figure, etc., right? So there's usually what people will talk about is a figure of merit for the LNA, which looks something like this, right? So this, again, I mean, the usefulness of this is to see what is hard, right? So increasing frequency is hard, increasing linearity is hard, increasing gain is hard, right? Decreasing PDC is hard, decreasing noise factor is hard, right? So if you have a good figure of merit, you're basically, these are the constraints that you're operating under, and usually it also means that there are trade-offs associated with all of these, that if I want to get high linearity and at the same time I want to get low noise figure, there is a trade-off space associated with it. It's tough for me to do that, right? Usually you burn power for dynamic range, right? So this PDC, you are burning not to get low F or low IIP3, you're sort of trying to burn it to get both F and IIP3 at the same time, right? So again, there's not a magic bullet to design here. You just design, see the trade-offs, and then build stages based on what the system calls for. So there is quite a systematic approach to the design of low noise amplifiers when we are dealing with, if we have a transistor, right, and we have what are called the noise parameters of the transistor, right, then there is a systematic way to design the LNA to achieve optimum noise performance, right? We are going to talk about it just at a high level, and I'll skip some of the derivations and give results, but hopefully we'll build some intuition along the way, right? So when we are in general trying to model a noisy block, right, we'd like to model this block ideally in terms of some voltage noise, right, and some current noise, and then have a block that is noise free, right? And if we are able to build these input referred noise, current, voltages and currents, right? Then analysis becomes very easy, and from a noise perspective, all we have to do is analyze the noise up to this plane, right? Because beyond this plane, the SNR is not going to change. Because the signal will get amplified, the noise will get amplified, the SNR will not change, right? So we just have to get the SNR at this point if you are able to make this model, right? One key insight into noise modeling, I'll just highlight here. We know that if I have a MOSFET, right, we let's say just a simple analysis with just a resistive load. Let's assume that everything is, there is no other source of noise other than the 4kT gamma GD naught noise, that is the IND squared noise, right? If I consider this to be my noisy 2-port, right? So this is the plane of noise in the system, right? Then I'm trying to model this with noisy with a noise model that looks like so. What I find is, let's look at what happens in this noise model. Let's see what happens in the real world if I short this input, right? When I short this input, right, I still see an output noise which will be 4kT gamma GD naught times RD squared, right? I'm ignoring the RO of the system, right? And if I leave the input open, right, I will still see 4kT gamma GD naught times RD squared, right? So whether I short the input or open the input, this is going to exist. Now let's say that I'm trying to model this without I'm trying to move all the noise to the input, right? So then I have this EN noise source and I have this IN noise source, right? And I have my noise free transistor, and this is my output, right? Now if I short the input over here, right, let's just, right? If I short the input over here, right, when I short this current will flow into the short and not create any voltage. So in this case, my my VN out short, right, will be En squared times GM RD the whole square, right? But if I open this, right, then what's going to happen is that if this current source was not there, if this noise current source model was not there, I would not get any noise in the system, right? In my this model, there would be noise in the system. So what you see is that you need the input noise model to have both a voltage source and a current source, so that whatever impedance you terminate with over here, whether a short or open, or if you analyze this further, if you place a ZS, right, what happens in the actual system must be what happens in my model. Does that make sense? So I need to make sure that my model is representative and correct, no matter what the output noise is the same, no matter what ZS is presented over here, right? So if I present just the short and the open were two examples of ZSS, right? And you can already see that without having both the noise current and the noise voltage, I will not get the right answer. But with the noise current present, then I can show that this will be 1 over j omega CGS squared times GM RD squared, right? So I can see that now since both networks are equivalent, I can equate the noise in the short case together to find out En. I can equate the noise in the open case to find out In squared, In, right? So then I can find out what En and In are. So now what happens when I actually terminate in ZS, right? When I terminate in ZS, I have to remember that this En and this In were actually generated from the same actual noise source. So it isn't that they are independent noise sources. They are correlated noise sources, right? En and In here are fully correlated. Now, this may not be true in all cases, right? In some cases, you might have some input referred current noise that is not correlated with the input referred voltage noise. In this case, because both En and In are representing the same noise source, you have to consider the correlation between them, and with a certain Zs, I cannot add them up in squares. I have to add them up in amplitude, right? So, if I have a certain Zs, right, and this is Em, and looking in here I see a certain Zn, right, and this is Im, the net effective voltage that I will see here will be In times Zn parallel Zs plus En times En times Zn divided by Zn plus Zs, right, the whole square. This will be my Vn squared effective, right? And I'm adding them up in voltage because in this case In and En are fully correlated, right? So it is not just enough to make the input noise model match what happens in the short and open case. It's also important to track what the correlation between the input noise models are in voltage and current in order to get the right or made the noiseless two-port match. So let's assume that this has been done in general for a device, right? And now we have a model in terms of the, so this is a noiseless two-port, right? And this noiseless two-port has been the noise in it has been represented in terms of En and Im, right? And I know some part of In is correlated and some part of In is uncorrelated, okay? So this is perfectly correlated with En, right? So I know this bit of information as well. I know what the voltage input referred voltage noise is, input referred current noise is, and I know what the correlation, which parts are correlated and which parts are not correlated. So in this scenario, if I represent I correlated as some white correlation, Yc times En, right? Then I'm skipping past the derivations, but what we can basically show is that the noise figure is 1 plus I uncorrelated squared plus Yc plus Ys. So if I'm driving this with a source that is Ys, right? And the source has a noise itself that is Is, right? So then I get this times En squared divided by Is squared. And now I can create some equivalent resistances and admittances. So I define Rn as En squared divided by 4 kT delta F, Gu as the uncorrelated square divided by 4 kT delta F, and Gs as the source noise equivalent resistance, right? So I'm basically representing all of these noise voltages and currents through equivalent resistances, right? And once I do that, and let's say that these parameters are available to us, what we can show is that the noise figure is given by this equation, right? And why is this interesting? This is interesting because once I've represented my input noise model, which we represented in terms of En, In, Iu, we just found equivalent Gu, Rn, Gc, right, or Yc. So once I've done that, what I see is there is an optimum source impedance that my two-port wants to see in order to achieve the minimum noise factor. Or to put it another way, I have this En and I have this Im, right? This is my model. If I want to get the best SNR in divided by SNR out, I should bring my input with a certain Zs, right? So there is an optimum source impedance that the device wants to see. Now this source impedance, notice, depends upon, so we can basically see that Gs is equal to Gc and Bc equal to minus, Bs equal to minus Bc, right? That's, oh sorry, that's not completed, there's an opt here. So Bs is minus Bc, which we call the optimum source reactance, and Gs opt is square root of Gc squared plus Gu over Rn, right? So I'm getting an optimum source impedance that I want to see, and this source impedance is completely dependent upon my noise parameters, right? It depends upon what Bc is and Gc, Gu, Rn are, which are all coming from the equivalent resistances of my noise model. They've got nothing to do with my power match at all, right? So then this wants to see a certain Zs opt for minimum noise, right? And it might want to see a different Zs opt for conjugate match. Right? So my was that question? Okay, my input. So since it wants to see a certain optimum impedance, it might be my source has an impedance Z0, right? And then I have to build a matching network, and that drives my amplifier, my LNA, right? But what should I match to here? Should I match to should I convert the Z0 so that looking in here, I see Zs opt that gives me the minimum noise figure, or do I convert it to Zs opt that gives me the best power match, right? That's the design trade-off that we have. We can look at it a few different ways, right? One way to think about it is that we can express the noise factor, this equation, right? You can you find that you can express it in terms of F min, which is the optimum lowest noise factor that you can get, times Rn over Gs divided by Gs minus Gs opt plus Bs minus Bs opt squared, right? So what this is saying is I get the minimum noise figure plus some degradation when my Gs is not Gs opt, when my Bs is not Bs opt, right? And the amount of degradation that I get, so if we think about this from a Smith chart perspective, right? So let's say on the Smith chart for the optimum noise, I might be supposed to be over here, right? But what this is saying is that when I am moving a certain distance away, and let's say that I am going to power match and I am going to be over here, right? So there is this much separation between them, and this quantifies how much noise figure degradation that I have, right? So I can either say I'll accept the degradation. So no big degradation is occurring because let's say this Rn over Gs is small, right? So I can live with that, or I can try to change my design in order to accept, to make this trade-off better. The key thing to note over here is that it's not that we have a single device, right? We have a transistor where we can vary W, we can vary V bias, right? So we can do both of these things to try to see which is there a better point where I am able to achieve both these things at the same time, right? That would be my ideal case scenario. So then we think about seeing if there is a systematic way for us to get both noise optimum and power optimum at the same time so that we don't have to make this trade-off, right? And several textbooks have these parameters derived in terms of, so in the transistor itself, we have primarily sources of noise that are related to channel thermal noise, right? And then you have gate noise, right? And some noise because of parasitic gate resistances, right? So there are papers that derive what these parameters are based on these metrics. We'll take a more millimeter wave algorithmic approach, right? So what you can show though is that if you take just a single device and you try to find the optimum noise match, right? Typically, the transistor wants to see some source impedance that is higher than 50 ohms, right? But we are constrained to systems where we are designing with antennas that are 50 ohms. If you are in an application where the antenna impedance is up to you and you can control the interface, by all means, it is perfectly feasible to change the impedance looking into the antenna so that or change the impedance of the antenna so that it is presenting Zs opt and you are power matched at the same time, right? But what we can show is that if we derive this based on the transistor parameters, the one useful insight that shows up is that there is some constant of proportionality times f over f naught over ft, right? So what we basically generally see is that if we increase the ft of our transistor technology, right, we are decreasing f min, and as we increase the frequency of operation, we start losing a noise factor. Of course, this is the ideal device. As you change the frequency, you're also changing the passives, you're changing quality factor. So higher order things can happen. But at its core, then I shouldn't do things that degrade my FT, right? And we saw early on in the device that FT did depend upon RS and RD. There was a degradation that happened because of that. And particularly if I do anything in, I add additional CGS and CGD capacitances, I'm going to degrade my FT. So I should try my best to not do that, right? But from a millimeter wave perspective, we can do something a little algorithmic, which is I can take my device, right, and I bias it at a current density, right, that gives me the lowest noise figure, right, and we find that this current density, that there is a current density that is sort of constant for f min, right. So we can sweep the noise, we can sweep the current density through the device, and when we look at f min, we see a plot that looks something like this, right. So we can basically find the current density that minimizes f min, and once we do that, we can then scale the width of the device, right. So find I density that minimizes f min, right. Then scale the width of the device till the real part of the Z opt for noise is the Z naught that you are targeting, right. And at that point, what you have accomplished is that the transistor, if it sees a real source impedance of 50 ohms, it will achieve F min. We haven't yet considered the reactance part. And then there are theorems that show that if you do feedback, the optimum noise source impedance is not moved, the real part is not moved. So you can put an inductance, a source degeneration inductance here, right? And when you put a source degeneration inductance, then what happens is that the real part of the impedance looking in here is GMLS over CGS. Right? So if I now make this equal to Z naught, right, I have created a situation where I know that for conjugate matching, this impedance looking in this direction must be the real part of Zn, right? So I have satisfied power match and I have satisfied noise match at the same time using this topology. So this is the source degeneration LNA, right? That is the it's a very popular design choice at millimeter wave, right? And you can the trade-off space though here is that this in this source degeneration LNA, right? The Z in that I see over here is S times Ls plus S times 1 over SCGS, right, plus GMLS over CGS, right. So I can make this real part 50, right, but this network resonates only at one frequency, right. So as a result, what I have is a narrow band power match, right. So this kind of source degeneration LNA is a narrow band LNA, but you can get quite low noise figure using this topology. And while it is narrow band, you can think of the Q as basically Z of the order of Ls omega over Z naught, right? That is a sort of Q. Actually, I mean, I guess very often what ends up happening is that you need, in order to resonate it, you need to have a series inductance here as well, which is Lg, so that you, when you look in over here, what you will see is Ls plus Lg plus 1 over SCGS. Let's call, let's call this over here Zn and this over here Zn prime, right? So Zn prime will be this, right? So your design equation will become S times Ls plus, or let's write it this way. GM LS over CGS is Z naught, and we need omega naught squared is 1 over CGS times LS plus LG, right? And there are of course second order trade-offs associated with this, which is that as you increase LG, right, some series resistance RG is going to start popping up here, right, which is going to introduce some noise of its own. So there is still some design iteration that is involved here to pick good values, but this topology works well as a narrowband LNA, and still, like I said, the Q that we can think of is of the order of omega times LS plus LG, right, divided by Z naught, right, of that order of magnitude. So it can still be reasonably wideband in the context of millimeter wave, that the fractional bandwidth is still wide enough for your application, right? However, there is interest in doing wideband LNAs at millimeter wave, right? I just sort of highlighted this source degeneration topology. It's again quite well known and covered in textbooks, right? So, and it is a workhorse. It's a very, it's an excellent topology that works very well in practice in terms of layout and all those things as well, right? Other approach that we'd like to look at millimeter wave, or is increasingly being looked at millimeter wave, is to make a more wideband input match and still optimize noise figure. So at lower frequencies, this kind of wideband input match is typically done through resistive feedback LNAs, right? At millimeter wave, the capacitances are large enough that just doing purely resistive feedback may not work. It depends on the frequencies and the device capacitances that you're working with. So what has become popular is to do transformer feedback, right? So there are papers by right, where the general building block is that I have this transistor, I place an inductance in the source, and then I have a gate inductance, right, and I couple through them through some K, right, and let's say that this is a n:1 transformer, right, and when I do this, if I made some assumptions, so clearly, I mean, this kind of topology benefits from having high n, right, but there is limited ratios that you can get on chip. But let's say that if K is approximately 1, right, if you assume very tightly coupled transformers, then you can show that the input resistance, in order to satisfy Z0 to be matched, you have to have an equation that looks like this, right, where this is the GM of this transistor, right? And what you have is also that your noise figure is 1 plus some factor that is, let's call that factor K again, that is 1 plus K over GM, something like that. So you basically want to increase your GM in order to bring your noise factor down, right? But you are constrained here because if this didn't exist, GM would just have to be 20 millisiemens for 50 ohm match, right? But because this N exists, right, So let's say, for example, that n is 2, right? So then you have half times 3 over 2 times gm, right, is z naught. So then you basically have 4 over 3 gm is z naught, right? So then gm can be a little bit higher than what it is if this feedback network, if I mean this for, let's say, common gate, right? If I directly match to common gate, this would be true, right? In this particular case, if I'm able to increase n, this can, if the higher I make n, the higher I can make gm, and the lower I can make noise figure. And this kind of topology, because it depends upon the input impedance depends effectively like a 1 over gm sort of matching network, right? You get wideband matching compared to source degeneration. There's been also follow-on work where instead of doing this feedback across the source, I can remember the source current and drain current are related, right? So instead of doing this kind of transformer feedback across the source current and degenerating, I can do the transformer feedback from the drain. So and if I do it across the drain, then I'm quite sensitive because there is gain from input to output, right? So instead of doing it across the drain, what they suggest doing is doing it at the cascode node and then making a ZL, right? So now these two inductors are coupled with a certain K, right? And you still again have a n:1 going this way, right? And with this type of topology, what you can show is that the Z naught, again, if K is 1, you can show that Z naught is, in this case, I guess n over gm1, right? So basically what we get as a benefit here is that if we double n, right, get n of 2, we can increase gm by a factor of 2, and we still have the same sort of equation there, which in noise, when we analyze the noise, there's a 1 over gm dependence, right? So in all of these LNAs typically that are matched with 1 over gm, there's always this concept of gain boosting, where what we are trying to do is be input matched, but at the same time use a larger gm, because the input referred voltage noise is 4 kT over gm, right? So I want to increase the gm, but I can't because the gm is constraining my matching. So these kind of topologies help you break that trade-off to some extent, right? So get wideband match, still use higher GM than just constrained to be 20 millisiemens, and be able to get a good noise figure. So this transformer feedback topologies actually look quite promising at millimeter wave, and have been implemented successfully. There have been more recent efforts where people are extending noise cancelling topologies. So traditionally, what at lower gigahertz frequencies, the way that we address this bandwidth and noise figure challenge is that we use the principle of noise cancelling, where the general idea is that I want my LNA to be matched to 50 ohms, right? So there is some circuit, let's say quite simply a common gate transistor, right? For example, which is providing my 1 over GM match, right? And then what I do is I find some way to cancel the noise that is associated with this particular 1 over GM stage through some other amplifier, and then I start getting limited by the noise figure of this amplifier. But the nice part is that this amplifier can be designed with high GM, right? So that its input referred noise is low because it is not constrained by matching. So matching is coming from this, right? And its noise is getting cancelled. So that gets me wide bandwidth and low noise at the same time. But the cost usually is power consumption, right? So what we see now is that at millimeter wave, such topology is also appearing where we have noise cancelling using this type of transformer feedback approaches as well to get wide bandwidth and low noise figure at the same time. So from a system perspective, we've seen numbers like 2 to 5 dB when we build LNAs at these frequencies. See the kind of topologies that have been adopted and the choices that have been made to build some large scale arrays. So if we let's begin with an old array that I was involved with in designing, right? And the choices here, for example, this was a source degeneration LNA. We used RTPS to provide 180 degrees of fine phase shifting. We used a VGA, which also provided variable gain through current steering, and at the same time could switch the input 180 degrees. So combine those two functionalities into one element. As I had shown earlier, we used a hybrid passive and active combining network, and this was an RF in IF out system, right, where we actually have the mixer on the chip, but the PLL that is and the frequency synthesizers that are operating at a lower frequency, and then instead of a doubler, we use a tripler in this particular implementation to multiply the LO and provide that to the mixer, right? And while not shown here, there was some level of IF and baseband filtering, right, in order to get to the output. So this architecture is a single 16 element array, right? And then following on, we looked at architectures that could be scalable as a unit cell tile, so that what I'm trying to build is a large scale array. So while this has 100 patches, only 64 of those patches are excited by actual elements. The others are sort of dummy patches, right? And what we have in this 94 GHz array is 4 ICs. Each of these ICs is driving a subset of the elements, right? And you can build a larger array then by taking this tile and placing it next to each other to synthesize a larger element array, right? So we built a scalable approach. The front-end design choices were quite similar to the IC that I showed. But in this case, we also, since the TX and RH was on the same IC, we had TX TR switches that were included, right? And a popular approach at these frequencies to do TR switches is that you have the antenna and then you have a lambda over 4 line, a lambda over 4 line, right? And then if let's say this is the RH side, when I'm shorting this to ground, over here I see a high impedance, right? And so the signal goes through and vice versa, right? So this kind of approach gives me good isolation and good loss. And what you can actually do is start integrating some of these things inside the design itself. So in here, for example, we didn't implement 2 switches like that, but we just effectively have a short over here where when the PA, it's operating in receive mode, we close this switch. So this impedance over here becomes high and the signal goes through to the LNA, right? So The one other thing to worth noting here is, in order to get lambda over 2 pitches, right, you have to make the number of the size of each particular front end IC very, very small. And so if we see over here within 1.5 by 1.3 millimeters, we are placing a TX and an RX, right? And if you see the passive choices, they're all done using transmission lines, right? Again, because we felt like we were being very aggressive about the layout, and placing transmission lines running next to each other, we felt was more reliable simulation than placing inductors and then have them coupled to each other, right? But I mean, such a design can be and has been done with inductors as well in following years. For this kind of switch-in application, right? So this approach works, right? Because this node, which is the input to the LNA, is actually shorted when this TH signal goes through, right? And what you see is an infinite impedance on when so Z in Rx is high, right, when this is shorted. So firstly, low power goes in, and then right at the input to the LNA, you're shorted in, low impedance anyway. So the voltage swing is reduced. This was at 94 gigahertz. It was in 130 nanometer CD. This is a nice survey that was shown in this paper, right, where what they have looked at is over time, right. So this was my PhD. So right at the bottom of the curve, but then it was early, so it has that going for it. What has happened over time is that we have basically increased the number of signal chains per IC, right? But there is a practical limit of 64 signal chains, because then the IC becomes very large, and you're also asking the question about how reliable your system is, because if one IC fails, you're losing 64 elements, so there are trade-offs associated with that, right? And also the reticle size of a mask in a CMOS manufacturing process, right, can be a constraint. But more than that, the real constraint is what is a commercial unit cell tile that actually makes sense, right? The other part that happens is that using these unit cells of phased arrays, how large an antenna are we building, right? And here we can see that folks are building. This is a little dated now, in the sense that, yeah, people were at 300, 400 element arrays with multiple ICs scaling to large antennas. But now we are at 700 to 1000 element arrays scaled with these unit cell tiles, and I'll show such a large array now, right? So the number of elements has actually even gone up further now to beyond 1000, right? So one of the real challenges in all this, and this is a very interesting number as well, is how many watts are we burning per centimeter squared, because we are trying to fit all these elements inside an IC. And as we increase frequency, it becomes a little easier to fit these elements because they are smaller. But then we are increasing the power density in our device, so we have to take the heat out in some way, right? So you can see here that there is a general approach which keeps it in the between double digits, right? And then the job becomes to design heat sinking approaches that can take the heat out of the IC. And so I showed some communication systems, and we discussed primarily communication system design, but this basically shows a radar array. And what is interesting to note here is that it's not really a phased array as much as a MIMO array, because you see a full signal chain in each of the RH chains, a full TH transmission chain in each of the TH chains, right? This was presented by Texas Instruments for automotive radar applications, right? And you can see some of the choices that are being made to generate quadrature LO phases. For example, they use a branch line hybrid coupler implemented using slow wave T lines so that it can be compact, right? And the choices on the LO path is that there is a 19.5 gigahertz LO that is distributed from chip to chip, and then there is on-chip frequency multiplication that basically gets you to the output 77 gigahertz to 81 gigahertz output. And this is again a interesting case study because it includes a lot of the digital signal processing for radar on the IC, along with this 4 RH 3TX MIMO radar front end effectively. And what we can see here is that the active circuits are occupying a fraction of the area, but the digital part and the digital area consumption is also quite sensitive. And here you can also see some of the trade-offs that I just described, which is that because this is, in this situation, the THs and RHs are operating at the same time, and you can have a strong coupling between them or reflection from bumpers or nearby objects. The receiver actually has to be very linear, and it has an input linearity of -7 dBm. So this is quite linear at millimeter wave, but the trade-off for that is that the noise figure is of the order of 14-15 dB. What is interesting is that the team published a follow-on paper a few years later where just improved transistor layout that basically got the transistor FMATs, right, led to better performance, and in this case the receiver noise linearity degraded 10 dB, but the noise figure also improved by a few dB in this publication. So yeah, you can start seeing the sort of trade-offs that people are making and the output powers that are being generated. If you remember right at the beginning for automotive radar, we saw that the ITU recommendations were around 10 dBm per element, and they are generating that with some margin here, right? And also you can see that these performances, because they are for automotive applications, are being validated at quite high temperatures to make sure that it is working in real world scenarios. And yeah, looking at more recent papers that are focused on the 6 gigahertz application with more compact architectures, you can see in 28 nanometer bulk, yet again, the VCO frequency is somewhere around 15 gigahertz, and there is a doubler that is used twice to get to 55. The interstage matching in all these stages is transformer based matching, right? And they were trying to target 60 gigahertz radar, and you can see again a similar trade-off between linearity and noise figure. And yeah, just to sort of come back to this one, you can start seeing that as the digital signal processing on these radar ICs increases, the radio is becoming an increasingly small part of the entire system, right? And a lot of it is DSP. Uh, Recently, there's also been a lot of interest in these kind of architectures, which are basically based on a scalable 2 by 2 array that is RF in, RF out, right? So these we typically refer to as beamformer ICs, right? And what they include is a 4-element beamformer. And so then what we do is on the PCB, we have power combining networks, right? So these red blots that are shown are all on the PCB. So on the PCB, there's a built-in power combiner with an isolation resistor that is placed, right? And we can build large arrays using this. And then right at the end, the combined signal comes out, let's say on the receive side. And we have and this is a sort of place where there is an option to put a filter in there, a single filter that is going to kill any spurious tones when the transmit side is going to provide some noise filtering on the receive side, right? And this kind of approach is quite attractive because no LO distribution is needed, right? But it relies on the fact that one is operating at frequencies where the power combiners can be built on the PCB, right? So of course, as we scale frequency, we can access more and more advanced interposer and PCB technologies to enable this kind of architecture, right? But one must also keep in mind that, for example, on the TH side, this is a fully passive distribution. So we saw that having a fully passive distribution impacted OP1dB, right? So this driver chip had to be really, really strong. So in some cases, what people will do is they will replace one of these with this IC itself as a distribution IC, and then you can work with it. So overall, of course, if I consider the total millimeter squared of silicon, right, this kind of approach usually takes up a larger area. Because each of these ICs has a lot of overhead associated with it, right? So overall silicon area is larger, but it has this benefit of scalability that I can build a 256, 64, 512 array all with the same unit cell and just keep scaling it in different dimensions. And if we look at the individual design choices for the sort of amplifiers and LNAs and PAs, we can again start seeing topologies that we discussed, source degeneration over here, transformer wideband batching, cascoding in order to get larger swing. So, and the kind of metrics that we are discussing, which is having good AM/AM and AM/PM in the design. And the architecture of the IC itself is relatively easy to analyze, right? Basically, we have the LNAs and PAs and phase shifters in each path, and then a switch that for a TDD system goes between the LNA and PA, so that the distribution network and the combining network, which is passive, can be shared between the THs and RHs. If in this kind of distribution network I had to build a transceiver with a TH distribution and RH distribution separately, that would be quite challenging. This is an interesting paper that came from Broadcom, where again they were, as you can imagine, in all these cases, doing the right partition of the IF, RF, ADC, array scaling, all of these are the sort of design choices that people are making. And in this paper, they did something interesting where they have a single coaxial cable connecting the phased array IC, right, which is the antenna array, with their IF IC. And this way, let's say there are multiple phased arrays feeding this IF radio. all of them require only one cable, and inside that cable they do frequency division multiplexing in that cable. So they are transmitting IF information at some frequencies, control information at some other frequencies, clock reference at some other frequency. So inside this chip they have a triplexer, right, which is going to basically take that input and split F0, F1, F2 signals out in different to different paths, right? And this would be your reference path, this would be your control path, and this would be your IF signals, right? So this kind of single wire interface is actually quite useful to do. If we look at the circuits themselves, we see again similar choices, right? For example, what you see here is a LNA with source degeneration, but this time instead of implementing it with the inductor, we implement it with a shorted transmission line because it can be modeled very well, and that effectively looking down we saw is just an inductor, right? So you can build source degeneration with that, and then you get to the output and you start transformer coupling. If you look at the PA structure, again very similar to what we've been discussing, right? And just as a point, I should add that when we are doing transformer coupling, what is convenient is that you can take the midpoint of that transformer coupling and use that to provide your supplies, right? This has a nice advantage because now you can build these supply and bias networks with low impedance, because this node is an AC short, right? So a differential, it's not going to matter. And because you can build the supply and bias networks with low impedance, you can reduce the memory effects in the PA. We talked about AM, PM, but there is another higher order distortion that happens in the PA, which is called memory effect, where the PA's nonlinearity depends upon the prior signals that went through the PA, right? And these kind of memory effects are associated often with the bias networks. So making low impedance bias networks is generally considered good practice to avoid memory effects. So those type of choices have been made in this array. And just to sort of highlight the packaging here, this is the a typical approach for packaging such large arrays, which is that the IC is flip chipped onto a sort of interposer which has the antennas, and from the antenna substrate you have a BGA that is then coming on to your conventional PCB, right? But in the array, that the 2x2 array that we talked about, there the frequencies are low enough that on your PCB itself, right, you would just have multiple ICs that are directly flip chipped on, right? And then you would have all the routing, etc., in multiple layers of the PCB. So in that case, you can also imagine that the carrier PCB for that large array is quite complicated and has a lot of layers to accommodate all the RF and power lines that are going through. So yeah, I mean, I think that's, you can see some measured antenna patterns that are interfaced to this. So overall, I'd say that, yeah, from an IC and packaging perspective, there's a high level of complexity to systems that are operating below 100 gigahertz. Above 100 gigahertz, things are still, being developed. But the applications, as they catch up, we'd expect to see more and more millimeter wave systems being deployed. So that's the material that I had. So thanks very much for your attention. And yeah, it's been a very good 5 days of review for me. I've learned a lot putting this course together. So thanks very much, and hopefully you found it useful as well. Thank you.